Today we study divide and conquer. When an algorithm contains a recursive call to itself, its running time can often be described by a recurrence. This is an example of a recurrence. A recurrence is an equation or an inequality that describes a function in terms of its value on smaller inputs. Look at this. N over 2 is smaller than n. So this recurrence looks very familiar to us, right? Park Jong-hoon. Okay, can you understand what this recurrence is? We saw this recurrence before. What does this mean? Yes, more exactly, we divide the whole array into two subarrays and then run merge sort recursively on each subarray. So we run twice. So this is the meaning. And how about this? What is this? Yeah, to merge two sorted subarrays. Okay. In this chapter, I'll explain how to solve recurrences. Solving recurrences means obtaining asymptotic bounds on the solution. Asymptotic bounds are big O, omega, or theta, so which I explained in the last lecture. And there are three methods to solve recurrences. First one is substitution method, and the second one is recursion tree method, and the last one is the master method. But I will not explain the master method. I'll explain only the first two methods. Before I explain them, I'll explain some assumptions. The first one is the assumption of integer arguments. Look at this recurrence. The real recurrence for merge sort is like this. So it's different from this. Why? Why do we need these ceiling and floor operators? Chang Yong-min. Why? 배민이. 신지수. 신지수? 박준규. 최소리. 김종빈. 신경식. So actually, n can be an odd integer. If n is even, this is fine. But when n is odd, then n over 2 is not an integer. So they are not divided into two same halves. One is bigger than the other. So to reflect that, the actual recurrence should be like that. But usually it is represented like this, because if after we solve the recurrence, the solutions of these two recurrences are the same. So we usually solve the simpler one. And the other thing is omitting boundary conditions. So in this recurrence, there are two parts. This is the main part, and this is the boundary condition part. To clarify that, its running time is constant when n is 1. But this is true for almost all algorithms. So we think this one is redundant. So we only show that in this form. Okay, now it's time to explain the substitution method. The substitution method consists of two steps. In the first step, we guess the solution. And then we use mathematical induction to prove the guess is right. Let me show you an example. The problem is determine an upper bound on this recurrence. This recurrence is t of n is twice t of the floor of n over 2 plus n. In the first step, we guess the solution. In this case, this recurrence looks very similar to the recurrence of merge sort. The only exception is the floor. Okay? So we can guess that the solution would be the same as that of the merge sort. So it would be big O of n log n. Then now let's prove this. Let's prove that t of n is big O of n log n. To prove this, what should we do? We usually do this. To show t of n is less than or equal to Cn log n, where the constant c can be selected arbitrarily. Why? 어미송. Can you explain why? 손광훈.
기구의 정의가 그래서 C랑 N제곱을 찾으면
Yes. The definition of big O is this. It's an asymptotic upper bound. So it means t of n is at most Cn log n for some positive constant c. Okay? So we are going to prove this. Now, we use mathematical induction to prove this. Mathematical induction is 수학적 귀납법. Okay? Okay, some students don't know the name. So after they listen to everything, they find out, oh, it's 수학적 귀납법. So instead, I will tell you first. 수학적 귀납법. And there are two steps. In the first step, we show the basis or boundary conditions is true. And then inductive step. Inductive step is like this. Let me show you one. Basis is such as assume that we are going to show this is true for every positive integer n. Then the basis is show that it is true when n is 1. Okay? Then the right-hand side is 1, and the left-hand side is also 1. So this equation is true. This is the basis. And then the inductive step is, first, we assume that this equation is true when n is k. Then from this assumption, we get this. Okay, this is assumption. From this assumption, we show this equation is true when n is k plus 1. Then the step is just add k plus 1 to both sides, and then by some calculation, we get this. So once we have this and this, we showed this is true for every positive integer k. Okay? This is the mathematical induction. A more general mathematical induction is like this. It is true when n is less than or equal to k. Then we show n is less than or equal to k plus 1. So there are some variations, but the basic idea is the same. In this case, look at this recurrence carefully. The recurrence is like this. T of n is twice T of the floor of n over 2 plus n. Okay, this is the recurrence. So in this case, we assume that, and we are going to show T of n is Cn log n. We are going to show this using this recurrence. So, and I will show you the inductive step first. In this case, we assume that this is true for this value. Assume that this bound holds for the floor of n over 2. It means T of the floor of n over 2 is at most C, the floor of n over 2, log the floor of n over 2. Okay? This is assumption. Then I have to show this. Okay. And look at this page a couple of minutes and try to understand the proof. How can you get this first inequality? Can you explain? Yes.
위에 식에서 2만 하면 되는 거 같습니다. 그러니까 옆에 있는
Yes, by replacing this term by this, we get this inequality. Okay? And then from this part, we can safely remove and think of another expression without the floor. Is it bigger than this or smaller than this? After getting rid of the floor. Do you know the floor? The definition of floor? 버림. Then it's bigger. Without the floor, it gets bigger. Then after getting rid of the floor and then cancellation, we get this. Okay, and the property of the logarithm, we get this. And note that LG is log base 2. So this is 1. So we get this. So up to here, we have this. Up to this line, we proved this. But what do we have to prove? We have to prove we have to show this. Okay? This is the aim of the proof. So, if this is bigger than this, it's done. Let's say this value is A and this value is B. Then if A is smaller than or equal to B, the proof is completed. Okay? So, to satisfy that, C should be 1 or more. So if C is greater than or equal to 1, this proof is correct. Okay? Then let's get back to the boundary conditions. Usually, the boundary condition is satisfied when n is 1. But in this case, it's not true. Look at this case. T of 1 is positive. It's the running time of an algorithm when it has only one element as input. So it is positive. But the right-hand side is Cn log n. So when n is 1, the right-hand side is always 0. Okay? So you cannot satisfy this inequality with any value of c. So we cannot satisfy this when n is 1. Then let's find the next basis. Let's try 2. The advantage of the big O notation is we don't have to stick to 1. We can increase 1 by 1 until there is a value of n that's satisfying this. So try 2. Then by some calculation, we can show that for some value of c, this is satisfied. Okay. So I explained how to prove a recurrence when you have a guess, when you have a right guess. Okay? But how to guess a good solution? We can do it using the recursion tree method. Then let me show you how. Look at this recurrence. The recurrence is T of n is 3 times T of the floor of n over 4 plus theta n squared. So this recurrence doesn't look familiar. Okay? This is quite complicated. So I'll show you how to guess this solution. I will show you that it is theta of n squared. Do you still remember what the theta notation is? Kim Hyun-jun. Okay. What's the meaning of T of n is theta n squared? Can you still remember the meaning? It was, you learned it 2 weeks ago, so 2 weeks is a very long time. Okay, then what is the meaning of this? T of n is big O of n squared. 정명수. N is smaller than n squared. N? The degree of Tn is smaller than or equal to 2. So the degree of T of n can be 2, 1, or something else in between, or less than 1. Okay? So, 최영준, what's the meaning of this? 한상현, 오메가, smaller or bigger? Bigger. The degree of Tn is at least 2 in this case. 2, 3, 4, something else. Or 2.1, 2.2, anything. So if we show that T is omega of n squared and big O of n squared, it is to show that T of n is theta of n squared. So I show these two things. But the first one is very simple. Why? It is very obvious. Why? 강인구. 박성현. Why? I mean that we have to show this. We are going to show, we are going to prove this. But proving this directly is difficult. So we've proved this, and the conclusion is this. So I'm asking you, how can you find T of n is omega of n squared? 윤호상. It's not difficult. You don't have to use any method. 이선민. Yes. Look at this. There is a quadratic term here. So, the degree of T of n is 2 or more. Okay? So it's omega of n squared. Then the difficult part is showing this. It is bounded above by n squared. Okay, then we have to use recursion tree method to show this. When we use the recursion tree method, we first simplify the recursion. As you know, this method is used to guess the solution. So we only consider the simplest case. So we assume that n can be represented by 4 to the k. Then we can remove the floor sign. And the theta of n squared is replaced by cn squared. I don't know exactly what is here. It can be any quadratic function, but I replaced it by one of the simplest quadratic function. when T of n is 3 times T of n over 4 plus Cn squared. Then this is the recursion tree from this recurrence. And I explained this recursion tree before when I explained the recurrence of merge sort. So look at this recursion tree for a while and to understand the meaning. Yes, this recurrence says T of n is the sum of these 4 terms, 3 terms plus this. So the same idea, but it is represented by a tree like this. Cn squared and 3T of n over 4. And then next step, Ichiho. Okay, this one. How can you convert this recursion tree into this recursion tree? Substitute n over 4 for n. Then we get a recurrence like this. Okay? Using this recurrence, we can further replace each terminal by a subtree like this. And then we do the same thing repeatedly until the terminal term becomes T of 1. So we get this. And then what do we have to do now? Cho Jung-hwan, what should we do now? Yes, add all the values in this recursion tree. And look at this. They are all constant values, and note that T of 1 is constant. Okay, so now we can add all the values. Okay. Then we add all the values in each level. And then add up all these values. Okay, then let's go step by step. It is Cn squared. There is only one term. And there are 3 Cn squared over 16. 3 Cn squared over 16, and there are 9. So sorry. So by simplifying this, we will get a equation like this. This term represents the summation of each level. And the number of levels is like this. Look at this. Look at this. The number of levels is log n base 4 plus 1. And I explained why it's log n, but the only difference is it's 4. Why it's 4? 최경렬. Why? Yes. The subproblem size is just 1/4 of its original size. 1/4 and 1/16. So they are divided into just 1/4 of its original size. So it's log n base 4. And another, so except the last level, the deepest level, there are log n levels. So it is represented like this. Look at the index. It starts from 0 and log n base 4 minus 1. So log n levels. And then add up, let's add up all the terms in the deepest level. How many T1s are there? Yes. Log n base 4. Why? Look at this. So the number of T1s is 3, 9, 27. So it triples level 1, level 2. So we remove the 1 because we start from here. So it is 3 log n base 4. And the property of the logarithm tells us it's n to the log 3 base 4. Okay? So it's this. Now we get this formula. And we can calculate this, but this value makes the calculation more difficult. So instead, we add all these terms when I goes to infinity. Okay? And then the calculation is simpler. It is like this. So it is 16 over 13 cn squared plus theta n to the log 3 base 4. And this is n squared. How about this? This is smaller than 1. So the degree of the first term is the degree of the second term. So this is removed. So conclusively, it is big O of n squared. We've come a long way to guess it is big O of n squared. Note that it is just a guess, not a formal proof. To prove that, we need to use the substitution method. It is given here. So look at this page for a couple of minutes, and I'll ask you some questions. Because we have to show that T of n is big O of n squared. So by the definition of big O, we have to show T of n is less than or equal to dn squared. Okay, another question. Why d this time, not c? We usually use c. Why it's d this time? Yes, there is c in the recurrence, so we need to use another constant. So that's why it's d, not c. Okay, then from this recurrence, we assume that this is satisfied when n is this value. So t of the floor of n over 4 is replaced by this. Then by removing the floor sign, we get this. And the calculation is simpler in this case. So we got this inequality up to now. And what we want to show is this is smaller than or equal to dn squared. Okay? Then from this, we can draw a condition. Okay? But this is right, but I think this expression is better. Why? Do you see the difference between these two inequalities? As an inequality, they are the same, but their meanings are slightly different. What is the difference? So up to now, what should we have to determine? What should we determine? The value of c or the value of d? The value of d, right. But this form looks like we are selecting the value of c. So it says d should be at least 16 over 13 times c. So this is better. Okay? C is a given constant value. And d is a constant, but we have to fix the value. So this is a better representation. Okay, now we show that t of n is omega of n squared and big O of n squared. So it is theta of n squared. Okay, I'll explain this another example in the next lecture. Any questions? Okay. This? Yes, why? Between this or between this? This? By replacing, the assumption is this is satisfied when this value is n over 4. the flow of n over 4. So there is an assumption like this. By using this assumption, we can safely replace it. Any other questions? Okay, then let's wrap up this class now and see you on Friday. After the class, feel free to ask me questions in Korean.